Okay, we're back. We're going to be working on voltage across the capacitor. So we've been talking about, most of the time we've been talking about voltage across the resistor and not the capacitor. This time we're going to be talking about voltage across the capacitor. Lots of tedious math. So here's the equation, the ratios of the impedances, and you crunch the numbers and you get this right here as the magnitude, expressing quality in omega naught, just like the formulas we've had before. We're going to change variables right there. That's what's going on. And little g is going to represent V out over the source voltage. So we can express it. So we take this right here and we convert it right down here. 1 minus u squared, which omega naught, remember omega naught is 1 over root LC. So omega over omega naught, this is going to be omega squared u. U squared is going to equal this. Absolute value signs, that's where we get this expression here. And I believe they forgot the square root. Oh no, they're taking the square of the voltages. Yeah, they're taking the square of the magnitude. G of u is the square of the magnitude. So this is perfect. This is perfect. For the imaginary part, they have to do this. They use the Q expression. And U over Q gives you the magnitude of this omega CR squared. U is omega over omega naught, and then the CR 1 over Q, the CR comes out to the top. So we can, it's pretty straightforward to go from this expression here to this. And I've just been talking it through just a little bit. So you guys can sit down and think about it a while and figure it out. Now, then we differentiate. Derivative of 1 minus u squared is here. Derivative of u over u squared over 2. Derivative with respect to u only is given by this. We set it equal to 0, so we solve for the equation. And we get this. It simplifies to this equation. And solve for the this is when the voltage across the capacitor is maximized, the conditions for when it's maximized. So we can find the omega when it's maximized. That's what omega max is. When is the voltage the maximum across the capacitor? And it's something less than the resonant frequency. A little bit less. Okay, and more substituting this back into the expression for G right here. Substituting it back in, you get this expression. Depends on the resistance. So, okay. So the voltage across the capacitor is a little bit different. Its maximum voltage is a little bit different. Now here's the expression for the voltage. Here's the expression for omega max. Expression for the voltage. Expression for the gain when at the maximum. when omega equals omega max. So here's a circuit, and you're expected to find these various things: the resonance frequency, the frequency where the voltage across the capacitor is maximized, given two different values of resistance, L and C. So I'm going to let you guys do this. Go to the handouts, go to the slides that are on my website. Now, I want to pick up on the problem I sent you guys to do. And here's the plots of it. So you might not figure these plots out, or you might not graph them, but I think it's instructive. It's interesting to note these graphs, that at resonance, and we've seen something similar to this before, at resonance you have a very sharp peak. You have a gain of approximately 100 with a narrow bandwidth. Half power bandwidth is like 70, what is it? It'd be somewhere around here. 3 decibels down. Half. In the phase, just flip-flops right here. With a large Q, a low Q, other way around, switch that. With a low Q, you get a big fat bandwidth, you get less gain, maybe 2, and a big fat bandwidth. Okay, so that's why people want this. They get a very narrow band pass. They can zero in exactly on the frequency you want. And remember that when you're designing things for use in the real world, you want to send things down a wire at a signal down a wire at a particular frequency, and you want to tune for that frequency exactly to reject extraneous noise. You want your information. You don't want everything else, which is why people do these circuits. This is an example, Tacoma Narrows Bridge. It was caused by aeroelastic flutter, so little energy was added each time to the swaying bridge deck. A little bit of energy was added by the wind. The wind was not a constant 42 miles an hour, which is it's not listed here. This is an electrical circuit model of what happens. So it plots what happens to the bridge at various frequencies, resonant frequencies. If the resonant frequency were just a little bit different, if it was stiffer, things like that. There we go. 42 miles an hour. That's where I got the 42 mile an hour number from. And it's not a constant wind. It's 42 mile per hour gusts. And each gust was about 5 seconds apart. That 0.2 of a hertz. And when it started gusting like that, we got failure. Okay. The model. Not much resistance to motion. It caused people to change. They stiffen things up, basically. They stiffened up the springy part of the circuit. This slide simply points out the similarity that, let's go here. When you flip, all these parameters, the equations are identical with the parameter substitutions. They look a lot alike. And this just writes down all the equations we've seen before, just puts it on one page. Okay. this is, notice in both cases, we have this. Okay, this is about time to end one video and go on with the next.